This is A-level chemistry 4.2, and this is looking at benzene and other compounds that contain benzene rings. So benzene is a molecule, a colourless liquid that was discovered in the 1800s, and it's got a C6H6 structure, and it's got an MR of 78. Okay, it's discovered as a colourless liquid used in what's it called? Flammable liquids. I couldn't remember the word then. So what happened was a man called Kekule, Auguste Kekule, thought that he had discovered it, or he thought he discovered the structure of it. So he believed that it was one carbon double bonded and then one carbon single bonded, and that's how it went. He believed that it could rotate and be an optical isomer, so sometimes the carbon would be carbon 1 to carbon 2 would have the double bond, and sometimes it'd be carbon 2 to carbon 3 and going around, etc. But the problem with that was that it doesn't readily accept bromine, so it should, with the double bonds, should be able to add bromine over the double bonds. So that was one reason why we didn't believe his structure. Another one was that we looked at its bond length, and its bond length should show that you've got one single bond, one double bond. However, all the bond lengths come out the same size, and it's kind of like an intermediate between a single and a double bond. Okay, it's also more stable when looking at undergoing reactions, bond enthalpy, breaking the bonds. What should have happened is that the double bond should have released 120 joules. However, so that means that it should have released 160 joules of energy. So when you were breaking all these bonds here. However, benzene only released 208. So there's a 152 difference. Okay, it's actually more stable, the structure that we actually know today. So Kekule was the man who thought he discovered it, and these are the reasons we use as to why he unfortunately was incorrect. So this is what benzene actually looks like. Okay, so benzene is an aromatic compound consisting of a 6-carbon ring with 6 hydrogens, and it's got a ring of delocalized electrons. Okay, so each carbon length is an intermediate carbon. Okay, the outer electron from the pi orbital of each carbon becomes delocalized to form a central ring of delocalized electrons, and that's its skeletal formula there. The ring structure is very stable compared to molecules of its size. Okay, anything that contains a benzene in their structure are known as aromatic or arene compounds. Okay, they have very high melting points, high stability due to their delocalized ring, low solubility with non-polar molecules. They generally can't be dissolved in water. Okay, this low polarity and high stability means that aromatic compounds resist addition reactions. Okay, that will require the stable delocalized ring to be broken. Okay, arenes tend to react by substitution mechanisms. Okay, so that's like an overview of what benzene is. You need to be able to comment on it, maybe in a little bit more detail than what I've done. But that is up to you to do a little bit of extra research by giving you an overview. Electrophilic substitution then. Because of its delocalized ring, the area in the middle with the p orbitals, overlapping, it's got an area of high electron density, okay? Which means electrophiles, which are electron loving, will want to attack the electron ring, okay? Partially destroyed, and then it is restored at the end of electrophilic substitution. So most of benzene molecules or aromatic compounds undergo electrophilic substitution, and there's 3 kind of main ones that you need to know about. We'll start off with the nitration of benzene, so that's adding a nitrate ion. Okay, what you have to do first is create this nitrate ion. What you do is you've got sulfuric acid and nitric acid, and you react them together, and you make this and this. Okay, and then you react that then further, and it breaks down into water and this nitron ion that you want. Okay, when heated with the benzene, the combination of the reagents leads to the substitution of the NO2 plus electrophile onto the benzene ring, releasing the hydrogen ion. Okay, so this is what happened. Because this is an electron dense area, it's really attracted to things that love electrons. Okay, so what happens is the delocalized electron ring gets destabilized for a certain period of time. It's not long. Okay, this is the longest bit here. Okay, that's what we call our reaction intermediate. And then that hydrogen ends up on its own. Normally that hydrogen then will bond by here and make more sulfuric acid, okay? This produces sulfuric acid. This is how the sulfuric acid is catalyst, since it's not used up. So that H then goes back up there, bonds to that. So then you've got nitrobenzene. Another thing then is Friedelcraft alkylation, okay? Again, it's a little bit different. This time, okay, we are adding a carbon on, so it becomes one carbon longer. You need an aluminium chloride catalyst for this. Same kind of thing is to create this positive nucleophile, which will attack this benzene ring, okay? Again, a hydrogen is lost out, normally binds by here, and you end up with aluminium chloride again, because it's a catalyst, and HCl, okay? So again, another way that you can add to benzene. And then kind of like the final way is the halogenation of benzene. Okay, in this mechanism, an unusual and highly unstable halide ion must form. So halide ions have a negative charge, but they have to have a positive charge to be able to attack this benzene ring. Okay, how they do this, okay, is they use a catalyst, either iron chloride or aluminium chloride, or if you're adding bromine, then bromochloride and aluminium bromide. Okay. If you're using iron, it needs to be at room temperature. If you're using aluminium, it needs to be anhydrous, so it needs like a dry environment, okay? What you have is you have your diatomic molecule, so I've used Br as an example, okay? Because of the presence of this positive ion, it creates a dipole. So the electrons move over here. So then you've got one electronegative bromine, and you've got your electropositive bromine, okay? In this example, they've used chlorine. It's the same thing, okay? Just make sure you don't mix up your catalyst. So if you're using chlorine, then use the Cl. If you're using bromine, then use the Br. This is how we create the electrophile, okay? It's got to have that positive charge. Same kind of mechanism, okay? The delocalized electron ring becomes unstable for a moment. You end up again with a hydrogen knocked off because the chlorine's taken its place. And again, the kind of thing that will happen, because what you will end up with from this is you'll end up with this positive, but then you'll end up with FeBr4, which is negative, okay? So that's then this compound here has been added to benzene. So then what happens is you make FeBr3 again, plus HBr. So that hydrogen from here will add on here to make these stable compounds, and you can reuse your catalyst. You need to make sure that you end up with whatever catalyst you do at the end, because you need to be able to reuse it. That's a property of being a catalyst, okay? So, last little bit then. When you add on a halogen, the benzene ring draws electron density towards itself, okay, and away from the substitute group, such as the halogen atom, okay? This is called a negative adductive effect. In particular, in this example, there is some overlap between the p electrons on the chlorine and this delocalized ring system, okay? It gives some pi character to the bond and it strengthens it, okay? So what essentially happens is it kind of like brings that in to its delocalized system so that you've got an even stronger bond, okay? As a result, the bond strength between benzene and the halogen atom is increased, making it less likely for reaction to occur as the molecule is more stable, okay? So it's quite a short topic, this. You need to know all about benzene and all about how we came up with the structure, and then the three kind of reactions of benzene.